Hi everyone, this is Mrs. GA, and today we're going to talk about transformations of functions, but first I'm going to need you to pause the video and try this quick warm-up. Alright, so go ahead and check your work. You'll notice that here I asked you to find the parent function for our quadratic function, which is y equals x squared. So we can always use a table of values to do this. This hopefully looks familiar. This is a parabola, which is the graph that is made from a quadratic function when x is being squared. And we are going to be transforming this type of function today, which is why I want you guys to kind of see what our parent function looks like. So notice that we do have a vertex at the origin at 0, 0, and then it does make this U shape. And notice that the vertical distance between the points is growing, which is what's causing that curve. So it's no longer linear. This is a U-shaped curved graph. And we will be coming back to these coordinates and back to our parent function to help us graph more complex equations. All right, so today we're doing just a really big overview of what are called transformations of functions. So understanding your transformation rules is incredibly important. We are going to come back to this every single unit. Every time we learn about a new type of function, we're going to use transformations. And the nice thing is the rules are the same for any type of function. So if you know these rules, you can graph just about everything. So some terminology first. Transformation is just the general word for a change to a function. So there are three main types of transformations we're going to be working with. First is called a translation, which is really just a fancy word for a shift. So you can shift horizontally, meaning left or right, or we can shift vertically, meaning up or down. The next is a dilation, which really we will be calling a stretch or a shrink, sometimes also called a compression. So I'll just use the words stretch or shrink, but it does just that. It kind of makes your graph stretch out vertically or horizontally, depending on where it is in your equation. And the last type of transformation is a reflection. So you know what a reflection is. You know, it maps your graph over a vertical or horizontal line. This can be done vertically or horizontally, and it will typically be done over either the x or y axis when we're working with our functions. So it's really important that we understand how to interpret an equation in terms of transformations. So first, we're working with let's just assume this function called f of x. So notice here, I'm adding some value, which I'm calling k, outside of our function. So anytime you are adding or subtracting, which you can see with these first four, adding or subtracting is always going to be a translation. Always, always, always. So all four of these are going to be translations. But depending on where they are being added or subtracted will tell you if it's vertical or horizontal. So anything that's done outside of your parentheses that's not directly affecting x, anything outside your parentheses is going to be vertical. So this is going to be a vertical translation. And since here we have a positive k value, it's plus k, this is going to shift our graph up. And then if you look at this next one, again, it's addition or subtraction, which is always going to be a translation. It's outside the parentheses, so it's another vertical one. Anything that's not affecting x, think of it as affecting y, so making it vertical. So this is another vertical translation, but because we see that it's minus k, this time it's going to shift our graph down. And it would shift down k units, whatever k is. Now here in these next two, you see that we are adding or subtracting again, so it's another translation or a shift. However, it is clearly grouped with x. So anything that is clearly grouped with x is going to always be horizontal. So this is horizontal because it's grouped with x, and it's a translation because I'm adding or subtracting. So both of these are horizontal translations. But just like when we were looking at the vertex of our absolute value graphs, anything that is grouped with x is always going to be and act in the opposite way. So although this says plus h, and when we think of plus, a positive direction is moving to the right, this is actually going to shift our graph to the left h units. So it's going to shift our graph left h units, and I'll add k up here. And then this one, since it says minus h, it's going to do the opposite, and it's actually going to shift our graph right h units. Okay, but just remember, anything involving our addition or subtraction will be a translation, which is just a shift. Anything that's affecting your y value or outside of your parentheses will be vertical. Anything that is directly affecting x, so clearly grouped with x, is going to be horizontal. Now let's look at these next two examples, or these next two transformations. So here you can see that we are multiplying part of our function by a constant. So anytime you're multiplying by our constant, that is going to be a stretch or shrink. Okay, now here you can see that we're multiplying outside of our function in front. It is not clearly grouped with x, so since it's out front, we will call this a vertical stretch or shrink. Now, to decide if we call it a stretch or shrink, we actually need to look at the value of a. One thing to note is that a will always be positive. If you see a negative, treat it as a separate transformation. So a is always positive. Now, if a is greater than 1, we would call this a vertical stretch by a factor of a. And if a is less than 1, so it's between 0 and 1 because it's always positive, we would call this a vertical shrink by a factor of a. Now, graphically, or the change to the parent function graph, when we have a vertical stretch, it actually usually makes your graph look a little bit narrower or skinnier because it's growing taller faster. And when you have a vertical shrink, it kind of makes your graph look a little bit wider or fatter because it is not growing vertically as fast. Sometimes it's hard to tell with this transformation, but it depends on the type of function how obvious it is. Now here in this next transformation, you see that I'm multiplying by a again, but this time it is clearly being multiplied to the x, which means it's going to be horizontal. Now again, here we need to know the value of a to determine if it's a horizontal stretch or shrink, and this one is even stranger. This one I'm going to put a little star by because it's extra weird. The factor, the stretch or shrink factor, is always going to be the reciprocal of a. It's always going to be 1 over a. So for example, if a is 2, it would actually be a shrink factor by 1/2, 1 over 2. So anything horizontal is always a little bit tricky. With the translations, it's opposite. With the stretch or shrink, it's a reciprocal factor. So that actually means that if a is greater than 1, if you take the reciprocal of something bigger than 1, it ends up being a less than 1, so it ends up being a shrink. So we would actually call this a horizontal shrink, and it will be by a factor of 1 over a. It's always going to be 1 over a. And if a is between 0 and 1, when we take the reciprocal, it becomes a larger number, so it's actually going to be a horizontal stretch by a factor of 1 over a. So really, you look at what 1 over a is. If 1 over a is bigger than 1, it's a stretch, and if 1 over a is less than 1, it becomes a shrink. Now, I think this is a little easier to understand when we're actually working with real values, but just remember that we have this special rule that it's a factor of the reciprocal. So in terms of what it does to our graph, if you have a horizontal shrink, it's like you're putting your hands on the outside of your graph and you're moving them together. So this actually makes our graph look narrower. And when you have a horizontal stretch, it actually makes it look a little bit wider because it's growing horizontally faster. Now the last two lines here, we have the same transformation, but it's applied in a different part. So anytime you're multiplying by a negative, it's going to be a reflection. So again, it depends on where you're doing it. If you're doing it out front, it's a vertical reflection, because anything out front will affect the y value, which is vertical. Now, if you think of what a vertical reflection does, it reflects like from top to bottom or bottom to top. So that's always going to be a reflection over the x-axis. And if here you're specifically multiplying x by that negative, it's going to be a horizontal reflection. And this will always be a reflection over the y-axis. So if it's vertical or if it's horizontal, it's going from left to right or right to left. So again, I know this is a lot of kind of rules to learn, but the nice thing is once you know the rules, you can apply them to any type of function. So just remember adding or subtracting, if you have that operation, it's going to be a translation. Always, you just have to see where it's being applied. If you are multiplying by a constant, it is going to be a stretch or shrink, or we could call that a dilation more generally, but I will always use the word stretch or shrink. Shrink and compression are also interchangeable. And if you multiply by a negative, it will be a reflection. And then your job is to decide on if it's horizontal or vertical, and by how much, if you have a translation or a stretch or shrink. All right, so first we're going to practice describing transformations. So first we're going to look at our function and see if we can determine what the parent function is. Sometimes we can, sometimes it will just be a general form. But here I see something being squared. So here our parent function, it's the quadratic function. So we're comparing this to the form with no transformations. So I see three things going on here. The first thing I see, I'm always going to do things with multiplication first. It's kind of like order of operations. We should always apply multiplication first. So since I see that we're multiplying by a value, I know that's going to be a stretch or shrink. Since it is clearly not grouped with x, right? It is not inside the parentheses. This is going to be a vertical transformation. So this will be a vertical stretch, and it's a stretch because this a value is greater than 1. And we say by a factor of 2. The next two things I see are both going to be translations because it involves addition or subtraction. So let's look at this one. This one is clearly grouped with x. It is also within the stuff being squared. So I know since it is grouped with x, it is going to be a horizontal transformation. So this is a horizontal translation or shift, and it's going to go to the right 3. And then the last thing that I see that we have this -6. It is clearly not grouped with x, so it's going to be a vertical transformation. This will be a vertical translation, again, because it involves subtraction. And this one is going to go down 6. So if I know what my parent function looks like, which we do, all we need to do is apply these three transformations and we have a graph of our new function f of x. All right, let's try another one together. So here we have an absolute value function. So our parent function would just be absolute value of x. So we can approach this kind of in two different ways. First, we could actually simplify this function because we can simplify some absolute values. So we know that the absolute value of -3 is just +3. So I can actually rewrite this function like this, and it is completely equivalent to this. So if I write it like this, I see that my first transformation would be this 3 out front. And since it's out front, it is not grouped with x, it is vertical. So this would be a vertical stretch by a factor of 3. And then I see this +4 being added outside of my absolute values. So it's going to be a vertical translation down 4. So I can describe them like that, or I could just keep the original form and describe the transformations from here. Now, if we're doing it from this form, there's actually 3 transformations. So we have that negative, and then we have the 3, and then we have the plus 4. So this negative, so since it's a negative, it's a reflection, it's grouped with x, so that means it's a horizontal reflection, which is always over the y-axis. So this is a reflection over the y-axis. Now, if you think about an absolute value graph, look, if you think back to the parent function, which remember is just a V shape with the vertex at the origin, if you take this graph and you reflect it over the y-axis, it's exactly the same. So this type of transformation actually doesn't do anything to an absolute value graph. And that's also why writing it like this or writing it like this, it's interchangeable, again, because this type of transformation is not going to affect our graph. But we would still include it if we were describing it. If you see it there, we need to describe it. Now let's move on to the 3. So it's still going to be a stretch or shrink, but remember this time it's horizontal. And horizontal stretches and shrinks, remember, it's by a factor of the reciprocal. So the factor is actually 1 over 3. And since 1 over 3 is less than 1, we would actually call this a horizontal shrink by a factor of 1 over 3. So if the shrink factor is less than 1, that's why it's a shrink. If it's the factor is greater than 1, we would call it a horizontal stretch. So always look at what the reciprocal is before you decide if it's a stretch or shrink. Now this plus 4 is going to be the same. It's still going to be a vertical translation up 4. So whether you write it like this or like this, either way is fine, and actually both sets of answers are correct. Just make sure if you keep it as is that you are describing all 3, and if you decide to describe it in this way, just make sure you showed that you rewrote the equation. All right, let's look at one more together. So here we actually have a function g of x that's just defined as a transformation of f of x. So in this case, our parent function is just f of x, so we don't know what family of function it is. It's just kind of in that function notation. Now for this problem in particular, there is a really tricky step that you absolutely need to know, and it will keep coming up over and over because it will make it, this is that more rigorous honors level. Anytime you have a horizontal stretch or shrink with a translation, the stretch or shrink needs to be factored. It needs to be separate from the shift. So anytime you see something like this, your first step absolutely needs to be to separate that 2. So I need to factor out the 2, and then it actually becomes x plus 4. So notice that the 2 is still grouped with x, like it's still within our function. However, I need to make sure that the stretch or shrink is clearly separate from the translation. So again, please, please, please put a star by this step, highlight this step. This is going to come up over and over and over, and you could definitely expect to see this on a test or quiz. You have to factor it out. Now, you need to do this before you decide what the transformations are. Now, if you don't do it first, you're going to look at this and say that it's shifted to the left 8 units. But in reality, it is only shifted to the left 4 units. So you absolutely have to do this before you do anything else. Now, once I've factored out my 2, now I can go through and kind of decide what my transformations are. So first I see a negative. It is clearly not grouped with the x, it's out front. So that's going to be a vertical reflection. And remember, for a vertical reflection, we're always going to say what it reflects over. And if it's reflecting vertically, we're going to say it's over the x-axis. The next thing we can talk about is that 2 will always do the things that are being multiplied first. So this one is clearly grouped it's within the function, it's affecting the x, so it's horizontal, and it will be a stretch or shrink. Now remember, the factor, again, is the reciprocal. That's another weird one. So the factor is 1/2, which would make it a horizontal shrink. So this is a horizontal shrink by a factor of 1/2. And then the last transformation we see is this horizontal translation. It's horizontal because, again, it's clearly grouped with the x. Anything with addition or subtraction is a translation. Remember, for the horizontal translations, it's going to move in the opposite direction. So this is actually going to move to the left 4 units. So again, always look for that first step of factoring out that a value, or sometimes it's called a b value. It needs to be separate from your h value. And there's always going to be people that forget this step, but you can expect it on every single quiz or test. All right, I have a couple for you to try on your own, so please pause the video and give these a try. All right, go ahead and check your work here. So both of these have that really important first step of factoring out that stretch or shrink. So for the first one, you can simply factor it out. So factor out the 3, and then you could describe it from there. And then you would actually have a vertical shrink and a horizontal shrink by a factor of 1/3. Remember that reciprocal. Or you can simplify this because it's an absolute value function, and you can move this 3 out front, and then you just have that single stretch by a factor of 3/2, and it does go right 1 up 2 either way. Now for part B, again, you have to take that same step. We have to first separate the reflection and the stretch from the shift. So I factored out -1/4. So for this one, there's no way of simplifying this out because it's just in that standard function notation. We don't know what type of function it is. So we'll go from here. It does have that vertical stretch by a factor of 2. And then it has a horizontal stretch because the factor is 4. And then it has that reflection over the y-axis, and then a shift left 4 and down 3. So if you forget that first step, your shift is going to be off. It's going to go in the wrong direction and by the wrong amount. So that first step is super, super important when you're deciding what your transformations are. So now we're going to talk about how we can actually use transformations to graph. So if you know what your parent function looks like, or you have coordinates from your parent function, you can graph any more complex equation using transformation. So first, we see it here, or we can determine that our parent function is just x squared. It's our quadratic. So here, let's fill out the table for our parent function. So just a couple points to the left and right of the origin. And we're actually going to transform the coordinates in the same way, using the same rules that we describe our transformations. So first I'm going to list out the transformations just for extra practice. I do see that vertical stretch by a factor of 3. And then I see a horizontal translation, and that's going to go to the right 2. And then we see a vertical translation down 9. And now we're going to use these transformations to transform our coordinates. So anything that's horizontal will affect the x value of our coordinate. So this is our only horizontal change. Now, if you want to move a coordinate to the right 2 units, you're actually going to add 2 to the x value. So in this open space, I'm going to write the rule x plus 2. I'm going to take all of the x values from my parent function and simply add 2 to them. So we get 0, 1, 2, 3, and 4. So those are my transformed x values, but now I need to transform the y values. So I'm going to look for any vertical changes. So we have the stretch by a factor of 3 and the translation down 9. So I'm actually going to take all of my y values and I'm going to multiply them by 3. So I could say 3p of x, or you could say 3y. And then we're going to subtract 9 from all of those y values to move them down 9. And we're always going to do anything with multiplication before addition or subtraction. So if you write it like this, you simply follow order of operations, and then you just transform your original y value. So you multiply by 4, so we get 3 times 4, which is 12, minus 9, so we have 3. And then we have 3 times 1, minus 9, so negative 6, and then negative 9, and then back to negative 6, and then back to 3. So these are actually my transformed coordinates. So notice, again, I'm using my transformation rules to help me move or transform my coordinates from my parent function. So now I'm going to plot those new coordinates. So we have 0, 3, 1, negative 6, 2, negative 9, 3, negative 6, and 4, 3. And we know that makes that U-shaped graph, just like our parent function. And there you go. Now, if you kind of think back to what our parent function looks like from the warm-up, you can see that this graph is, it's definitely a little bit narrower than our parent function because of that stretch. It's growing taller faster, and it has definitely been shifted to the right 2 and down 9. So you can kind of check to make sure that your transformations make sense for what graph you ended up with. All right, let's try another one together. So here, before I do anything else, I am going to take that really important first step that we definitely don't want to forget about, and I need to factor out that 1/2. So we have x plus 6. And then if you would like, which I'm always going to do with absolute values, I'm going to simplify because the absolute value of 1/2 is just 1/2. So I can move that out front. I'd say vertical stretches or shrinks are always easier to work with than horizontal stretches or shrinks. So whenever you can, I like to simplify it out. So now I can look at this and compare it to our parent function, which we can see is just their absolute value function. We can start by describing the transformations we see. So I see that vertical reflection. So that's going to be a reflect over the x-axis. And then we have a vertical shrink by a factor of 1/2. And then we have a horizontal translation, and that one's going to go left 6. And then we have a vertical translation up 4. So now we're going to take our parent function coordinates. So I'm going to fill out the y values. And then we're going to make our rules to transform our coordinates. So here I only have one horizontal change again. So that horizontal change is to the left 6. So I'm actually going to subtract 6 from all of my x values. I understand that in the equation it says x plus 6, but to move a coordinate, we would subtract to send the x value to the left. So this becomes -8, -7, -6, -5, and -4. And then we have 3 vertical transformations, a reflection over the x-axis, and a vertical shrink. So those will just be multiplied. So -1/2 times our y value. And then we would shift it up 4. So we're going to add 4 to it from there. And then we'll just go through with all of our values. So here, if I multiply by 2, we have -1 plus 4, which is 3. And then here we have -1/2 plus 8/2, so 7/2. Please get in the habit of using improper fractions, not mixed fractions, not decimals, okay? Here we have 0 plus 4, which is 4, and then again 7/2 and 3. And now we can go plot our transformed coordinates. So we have -8, -3, or positive 3, sorry. And then we have negative 7, 7 halves, and negative 6, 4. And there we go. So we have something that looks like this. And just based on what we've already learned about absolute value functions, this is graphing with transformations, but we should know how to look at this and say, okay, our vertex is negative 6, positive 4. The slope to the right is negative 1/2. The slope to the left is positive 1/2, which is exactly what we get. But again, here we're practicing using transformations to transform our parent function coordinates. So it's always good to have more than one way of doing things, and it just leads to, that deeper understanding of functions and how the equation relates to the graph. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check here. Please make sure you have the super important first step of factoring out that negative. So even if it's just a negative, it does need to be factored out. Now you could go from here, but you'll notice that all of this is just being squared, and you can simplify that. Squaring a negative just gives you a positive. So this is kind of like our absolute value function. Because of the shape of our parabola, a horizontal reflection over the y-axis actually doesn't affect our graph. So this and this are completely equivalent. So you might as well just simplify it. It makes it a little bit easier, one less thing to worry about. And so we have our 3 transformations. So I took our parent functions and I did x values plus 3, and then 2 times the y values minus 7. And here's our transformed graph. And you can see it does definitely look like it's been shifted right 3 and down 7. It's definitely a little bit stretched out. So it does match what we would expect to see from the equation. All right, so now we're going to kind of go backwards and see if we can use transformations to help us actually write an equation. So just looking at this type of function, hopefully we can recognize that this is a quadratic function. It's a parabola. So a few things that we notice. It's no longer facing up. It is actually facing down. So that tells us that we actually have a reflection over the x-axis. Another thing to notice, if you look at where your vertex is right here, and if you look at the coordinate that is 1 unit to the, if you travel 1 to the right or left, these coordinates right here. For our parent function, usually this vertical distance between this point and this point is usually 1. Like you'd go up 1 over 1. But here you can see that we're actually going down 2 over 1. So this tells us that we actually have a vertical stretch by a factor of 2. Now there's one other type of transformation happening here. You could see that our entire graph has been shifted. We know from our parent function, the vertex of our parabola used to be at the origin, but we can see that that has moved 3 units left and 6 units up. So we have translation 3 left and 6 up. And of course, the left one is horizontal and the up one is vertical. So now we need to add all of these things into our function. So I'll call it f of x. The reflection and the stretch are both vertical, so those are going to be multiplied out front. So I'll say negative 2. Now, the only thing that's horizontal here is that shift to the left 3 units. So that's the only thing that's going to be grouped specifically with x. And if I want to shift it to the left 3, I'm going to add 3 to x. And then since it is a quadratic function, I'm going to put my squared. So notice I grouped that with x and then it's being squared. And then I still have that vertical translation up 6. So I'll say plus 6. And there you have it. So again, we're really going based off what we know the parent function to look like to help us determine what our transformations are and then write it into the equation. All right, I have one for you to try on your own. So use your knowledge of what the parent function for absolute value looks like. All right, go ahead and check your work here. So again, we know that for our parent function, the vertex at the origin, so that helps me to see that we went to the right one and down 4. And then we also know that we can look at the slope of this line to the right to determine if there's a stretch or shrink. And for our parent function, usually the slope is positive 1 to the right, but here you can see that it's 2 over 3. So that a value out front is going to be 2 over 3, which gives us that vertical shrink. And then we do absolute value of x minus 1, so it's always opposite for the horizontal translation, and then minus 4 on the outside. All right, and the last thing we're going to do is we're going to practice creating an equation, a new function that transforms a parent function given the transformation. So here we have 3 transformations. We have a horizontal shrink by a factor of 2/3, a reflection over the x-axis, and we have a translation 3 units left, 4 units up. So first, if it's a reflection over the x-axis, we know that this is going to be a vertical reflection. So when I'm writing my new function, it says we're going to call the new function g of x, and we're transforming f of x. So we're going to make these changes to f of x. This is a vertical change, so I'm going to put the negative out front. And then we say f of, and then any of the horizontal things, the shrink and 3 units left is going to go inside the parentheses here. So remember when you have a horizontal stretch or shrink, the factor is always the reciprocal of what you see here. So if the factor is 2/3, what we see inside our equation or function is going to be 3 over 2. However, we want to make sure that stays separate from our shift to the left. So I'm going to add another set of parentheses here, and then we'll say x plus 3. You can leave it like this, or if you'd like, maybe in the next step, I'll just distribute and simplify. It doesn't matter either way, but when you initially write it, it needs to be separate. And then we do have, so this one was vertical, and we have one more vertical transformation, that 4 units up. So on the outside, I will then add 4. So this is totally fine for your final answer, or if you'd like, we can distribute within our function. So we could say 3 over 2x plus 9 over 2. Either way is completely fine. But just be careful. You need to identify if a transformation is horizontal or vertical. And notice all of the vertical changes went outside the function, and all of the horizontal changes went inside the function here. And do be careful with that reciprocal factor. All right, I have one last one for you to try on your own. So go ahead and pause the video and give this one a try. All right, go ahead and check your work. So I highlighted in blue all the vertical changes. So notice that vertical stretch by 5 over 4 says we multiply by 5 over 4 in front. And then notice I subtracted 1 on the outside to shift down 1. And then my horizontal changes, which go inside my parentheses, there's the reflection over the y-axis. And notice I separated the negative from the shift. So you need to do that in your first step. And if I want to go 2 units to the right, I should say x minus 2. You can leave your answer like this. You do not need to distribute the negative, but you absolutely can. So either way is fine for your final answer. All right, that is all for today's video. Thank you so much for watching.